Transportation is also a big thing to tackle while mitigating climate change. While we are developing better vehicle models, we can also greatly reduce the impact of transportation by predicting congestion. Congestion is a big problem in urban states, and like many other things, we can use machine learning to predict it as well. This is a normal traffic state. Let's say that the average speed here is around 40 kmph or greater. Now it becomes a congested traffic when the velocity dips below some expected value. The cars would be moving slower than average due to the congestion. So our problem could be simplified to just predicting the speed of the cars, and from this we could predict the congestion levels as well. But we need some input for that. How do you think we could go about getting that input? Could we use road cameras? No, because they would have to place a road camera on every single road, and we would have to go through extra steps to extract the speed from the videos. What about speed sensors? It is true that they give the actual speed, but like the cameras, we would have to place one on every single street. What famous technology that is widely available can we use for this? Global Positioning System, simply GPS. Also, we don't need to get GPS from every single car. We could use taxis which already use GPS for communications with consumers. This would be an average estimate for the congestion because we are only using a fraction of the vehicles. So our model goes something like this. First, GPS data is not spatially accurate because of its large scale. So we would need to map that data onto a road map. Secondly, we need to identify road networks, which means roads that have similar traffic and are connected to in some way. Then we have to get the average speed of the road network from the GPS data, and using that data, we could predict the future speeds of the road network. And if we found the speed, we basically have the prediction for the congestion level. From the GPS data, we get two things, the global position, and these positions are measured on specific time intervals. So we use the hidden Markov model for the GPS mapping part. This is another conventional machine learning method, and if you have probably noticed, conventional methods are harder to understand than neural networks. This is because every conventional method is different and uses different mathematical logic, but neural networks are more structured, thus are easier to follow. Like the hidden Markov model uses probability, unlike everything we have discussed so far. So rather than confusing you more, let's just explain what it does rather than how. First, we have the GPS data, which are represented as blue points. As you see, they are not on the roads, but close to some roads. What the model does is that it projects many possible positions of the vehicles. Here I have only shown some of the possible positions, which are orange points, but in reality it does many. Then it calculates the probability of each possible state, and the state with the highest probability is selected. After doing it for every single GPS point, we get a map like this. Looks really crazy, right? Now the road networks are selected based on similarities in the traffic. Here we are only showing two to begin with. Calculating the average speed is really simple. We have the global position and the time interval. So if we find the change in the position and divide by the time interval, we basically get the speed of one vehicle. Taking average of all vehicles will give us the average speed of the road. Now we come to the deep learning part. Let me show you an example of somewhat of an important step in machine learning called as pre-processing. We know CNNs are really accurate, but they only work good on image-like data. And here's our data. It is shown in the representation of a matrix, or you could call it a table as well. Here if you go horizontally, you increase 5 minutes in time in every step, which is the time interval. And each row contains car position values for one road, and we have q roads. What we do is convert this matrix into a space-time image, which is not a real image as we would have expected, but it is in the form of an image. Then we pass it through a simple CNN and we are done with the prediction. Let's look at another network type which we can use. You might know it as recurrent neural networks. As we have discussed in the second part, it works really well on sequential data. But we can control how much data goes in it every sequence. Here the input window is 6, which means that 6 inputs are given every step. Now RNNs have many forms like the gated recurrent unit or GRU, or long short-term memory module or LSTM. And I can't go in much detail about it, so just know that they add a memory module on top of the RNN so that the network can actually remember the sequence, which makes it more accurate. Now the final part. We have predicted the speed, but we still need to predict the congestion level. This would be specific to each city, as a very dense city would normally have slow traffic, but congested traffic would be slower than that. A different city would have different values for normal and congested traffic. We can initially assume that the average speed greater than, let's say, 40 km per hour is basically a free road, and speeds below 15 are heavily congested. We could later change this based on how accurate our model is. These deep learning models tend to be accurate if you use them properly. As you can see, they are all above 90% accuracy. And one more thing, here T doesn't mean time, it means that the input window size, or how much info is going into the network at each step. You also might have noticed that different models are more accurate on different values of input windows. So to get even better accuracy, we could combine all these models into one model so that we could generate accurate predictions for long, short, and mid-term data.